Okay. Is someone start the recording or should I start the recording?
I think it's already recording.
Okay. So I will start my presentation. So for today, I will present the Yolo-Nas, which is the neural architecture search, which is proposed by DESI AI on May 3rd, 2023. So what is the Yolo-Nas? So Yolo-Nas is a new real-time state-of-art object detection that outperform both the Yellow V6 and V8, and it has also a better mean precision and with a better inference latency. So this Yellow-Nas was designed specifically for production use because it supports like int8 quantizations and it has efficient performance. So this Yellow-Nas leverage the power of the NAS, which is the neural architecture net. So just to give some kind of motivation, okay, just to give some kind of motivation, in the past, architectures such as fast RCNN and Yellow has been one of the most famous state-of-art when it comes to object detections, but they have a small limitations such as detecting small objects, and sometimes they also struggle with localization accuracy. So Yolo-Nas was trying to improve this kind of limitation by detecting small objects, by improving localizations accuracy. It's also try to increase the performance per computation ratio. Okay, so what is the new thing in the Yolo-Nas architecture? So the new additional idea of the Yolo-Nas architecture is the NAS architecture itself. So the NAS architecture, it stands for Neural Architecture Search. So first, let's define what it is. Like, what is the Neural Architecture Search? So it's just techniques for automating the design of the artificial neural networks. So back in 2016, people, researcher in Google, they are trying to ask these questions. They are saying, can we build an algorithm that design novel neural networks architecture that can outperform the hand-coded one? The question is a very good question. They are trying to ask, can we build an algorithm that could design a new networks that could outperform the existing one? So why do we need it? Like, why does it exist? So as we all know, the neural networks are very hard to design because usually they require high effort. They are very time consuming because we have to fine tune every little hyperparameter just to see what kind of change we have, and they also require expert knowledge in specific areas. So we need this neural architecture search to find optimal architectures and also to find the best possible hyperparameters for different kinds of hyperparameters. It can be like a number of layers, learning rate, and other hyperparameters. So now we have to look what is the basic blocks of the NAS algorithms. So the NAS algorithm contains four major components. So the first components can be considered as like a search space. Search space is like, it's just a straightforward. It's just, it defines the types of neural networks that can be designed and optimized. It is also defined the set of possible operation that we can do to form like a valid network architectures. So the second one is the search strategy. Some people call it the model generator. So this is, it defines just the approach that we use to explore the search space. So this is, it's just generate sample populations of networks. So the main idea for this search strategy is to estimate the performance of the possible neural networks from its design without any kind of computations. So the third is the search algorithm. So the search algorithm, it just basically received the child model, which get from this search strategy. Then it will optimize to generate high performance architectures using the reward that it gets. It can be, the reward can be high accuracy or low latency. So the last thing is just the model evaluation. This is straightforward. We just use it for evaluating against the validation data. So This is the overall overview of the neural architecture search, which is taken from the paper which is published in 2016, the neural architecture search with reinforcement learning. So this neural architecture used the reinforcement learning approach. So first we have on the left side, we have the controller. The controller is basically trying to produce child networks with performance prediction or probability P. So controller produces a sample architecture A, which is a child networks, and also it include the probability P. So on the right, the search algorithm that I mentioned, it tried to train the child networks with architecture A to get accuracy R. Accuracy R is just manually given as a reward. We can change it to latency or to memory, doesn't matter. But for this particular example, they use accuracy R. So once we train this model, child networks, then we have to give some kind of feedback back to the controller. So the way we do it is we kind of compute the gradient P and we scale it with R, which is the reward we give to the model. So how does it work? So we have the workflow. First, the workflow is the controller is used to it's generate hyperparameters as a sequence. Then training in networks networks specified by the controller, the child networks will result in metrics. So this child network will be trained and it will have some kind of metrics. Then this matrix is used to update the controller. So it's just like reinforcement learning. We have to iterate through over and over to find the best possible optimal structures. So as I said, the reward can be different metrics. For example, it can be accuracy, it can be latency, memory, combination of different things. This is considered as like reward signal. So there is also optimization policy, an optimization problem under certainty, because we need to define its probability as well. And we basically what we are computing is three things. We are just estimating the performance of the child networks. The controller is just estimating the performance of this child network without any computation. It's just predict how it will perform. Then the second thing is we are just trying to predict the performance metrics from the child networks. So from this part, it just try to train the child networks, and it gets the metrics from that training. Then lastly, we are trying to use policy gradient to update the controller. So the controller needs to be keep updated to perform well. So this is also a sample image, which is taken from the paper, how controller samples simple convolutional networks. So as we can see here, for one layer, the controller can pick many different kinds of combinations. So it can pick different filter height, different filter widths, and also it can pick different kind of number of filters. So the controller has an option to sample different number of combination just to see which one is better for given metrics. So for the next iteration, the controller will give high probability to the architecture that receives better metrics. So if the accuracy is low for the first iteration, so for the second iteration, the controller will give high probability to the architecture that gives a better matrix. So the controller will learn to improve this search over time. Through iteration, the controller will converge to some optimal solutions. So we also have auto regressor controller, which means it just predicts a hyperparameter one at a time, and based on the previous condition, it will just try to predict the better one. So training speed, so to accelerate the training speed, we can just use parallelism, and we can just synchronous update. We can just produce a bunch of child networks, and we can train them simultaneously. Then we can update those together to increase the speed training. So what is the power of NAS? That's the question. So the power of NAS is cutting edge models. So the NAS can design a better, and that can outperform the hand design architecture. So that's the power of NAS. So also with no preparation. So NAS can build a good model from scratch, given a good search space. That search space has to be defined by the machine learning engineer. But once the search space has been constructed, NAS can be well designed a model from scratch. So it's also wide search space. We have if we design a space search space, we can have multiple hyperparameter optimization, different structures, different building blocks. So lastly, we can also custom reward signal. We can customize what kind of metrics we want. We can set it as accuracy, latency, memory, and different kinds of combinations. So now let's look at how NAS plays a role in coming up with the Yolo state-of-art model. So configuring Yolo search using NAS. So as I said before, finding the right architecture by hand is extremely tedious and inefficient. So they applied AutoNAC to discover novel object model detections. So what is AutoNAC? So AutoNAC stands for Automated Neural Architecture Constructor. So this is AutoNAC is DESI engineers. They come up with their own NAS algorithm, which they call it AutoNAC, which is used a neural design space, incorporating state-of-art architecture design principles and different kinds of elements. So in DESI research team, they come up with a new NAS algorithm that they provided for configuring the YOLO search. So to create the Yolo-Nas, the researcher team started with a search space of like 10 to the power of 14 possible architectures. As you can see, this is enormously huge number, which means they have multiple search space where they can just experiment which one works better. So they also use like AutoNAC engine. This AutoNAC engine traverse this search space, try to find the best possible novel architectures. They call this region the efficiency frontier. I will show you what the efficiency frontier later. So the AutoNAC explores and maps the efficiency frontier, searching for best possible architecture between latency and throughput. So they also sample 3 points from this efficiency frontier. They try to sample Yolo-Nas small, medium, and large architectures. So for the Yolo-Nas as well, they try to use quantization-aware architecture. So this is it just employs quantize-aware blocks and selective quantization for optimized performance. So this quantization use like skip quantization, because if they use the full quantization, the performance will drop, the accuracy will drop. So to solve this problem, they try to use a skip quantization to increase the accuracy. So they also use like int8 quantized version, but when you use this int8 quantized version, the precision will drop like a little bit, because they are using the int-based quantization rather than just the full precision or the floating point quantization version. So I think let's see this animation. So this is the high-level overview of the Yolo-Nas architecture. So as we can see here from the left, they define the neural search architecture. So this is the backbone. We have like stage 1, stage 2 to stage 8. So on each stage, the architecture can take up any kind of number. As we can see here now, 65, it can be 120. Like each stage have their own different combination or permutation that the neural architecture search can take from. Then it will just map. This is what they call it, like efficiency frontier. Efficiency frontier, as you can see here, is just mapping between latency and accuracy. So sampling different kinds of number of layers and convolution, they try to map it to the accuracy and to the latency. So as you can see here, they try to pick 3 top performing model. This is like Yolo-Nas small, Yolo-Nas middle, the Yolo-Nas large model. So the thing you see at the bottom here, the 2 boxes at the bottom, they are using quantized combined quantization. So the first model here is the quantization synthesis reparameterization, which is using reparameterization to decrease the weight of each layer to make it more efficient when it comes to performance. So this is also used like quantization channel interaction. They are trying to use like int8 version to increase its computation without losing a lot of accuracy. So the combination of this QSP block and QCI block, it will help to reduce the weight of the layers, because they can quantize it to make it smaller, to break it down to smaller level, to increase the computation performance. So when it comes to training detail, Yolo-Nas has multiple phase training details. So the training involves object like 365 Coco pseudo labels. They also use like knowledge distillations. So for the model is pre-trained on the object like 365 with 2 million images and 365 different kind of categories. And they also use like Coco data set, which is 123K unlabeled image. They also applied knowledge distillation by adding KD term to the loss function. This enables the student networks to mimic the logist of the Bose classification. So the reason they use knowledge distillation on training is to reduce the complexity of the model. So knowledge distillation, as we know, it will reduce the complexity by adding efficiency and speed as well. So this is a figure where they are trying to compare their own Yolo-Nas model and with the Yolo V series. So as one thing we can notice from here is the int8 quantization small Yolo-Nas has a better latency, but as we can see here, its accuracy drops a little bit because they are using int8 quantization, which decrease the accuracy, because they are not using a full precision, rather than just they are using like int bit formation for this quantization. But as we can see here, when they are using Yolo-Nas large, the accuracy increase like rapidly, but the latency will suffer a little bit. But in overall, their performance their model outperform the V series, as we can see from the figure. This is also additional figure they provided. They're trying to compare their model by using average precision. As you can see here, the Yolo-Nas medium has the higher mean precision comparing to other V8 and V5 and V7. So in conclusion, we can say this Yolo-Nas model offer the high latency trade-off comparing to existing detection models. It also have a highly effective and accurate, because it has a very high performance computation per ratio. And this is possible by using DESI's AutoNAC, which is automated neural architecture constructor, to configure specifically for the Yolo state-of-art models. So this is all about Yolo-Nas from me. Thank you for your time. And if you have any question, please, you are welcome.